January 1945. Altitude, 28,000 feet. The European winter hangs in pale layers over a continent in ruins. Sunlight cuts through scattered cirrus clouds, turning ice crystals into sharp glints against a silent sky. Then the silence breaks. A single streak tears across the upper atmosphere, too fast for a piston engine, too flat in tone for a radial roar. A Messerschmitt Me 262 flashes past the contrails of Allied bombers, its twin Junkers turbojets leaving thin white needles in the cold air. Gunners struggle to track it. Pilots lose visual contact in seconds. The jet dives, levels, climbs again, an aircraft moving at a velocity that war-era reflexes were never meant to follow. Below, the thunder of artillery continues its slow destruction. Above, a new kind of speed rewrites the meaning of air combat. The story of the fastest fighters of the Second World War begins with that split-second blur, an engine's scream that signaled the end of one age and the beginning of another. Speed shaped every front of the Second World War. From 1939 onward, nations treated velocity not as a technical detail, but as a strategic weapon. The aircraft of the late 1930s still followed design patterns rooted in the First World War. Metal frames, piston engines, propellers optimized for mid-altitude engagements. But within months of the war's outbreak, air combat changed. The Luftwaffe relied on the Bf 109, a fast, lightweight interceptor capable of pushing past 350 miles per hour. Britain countered with the Spitfire Mk XIV, a refined elliptical wing design that offered clean aerodynamics and formidable agility. These machines represented the height of pre-war engineering, yet even at their peak they revealed a limit that engineers everywhere felt pressing against the future. Propellers could only push so much air. Engines could only spin so fast before compressibility effects began to destabilize flight surfaces. The race for speed had reached a ceiling, and every major power knew it. By 1941, the United States entered the conflict, bringing industrial scale unmatched by any Axis nation. American engineers pursued a different answer. Instead of refining light interceptors, they expanded horsepower. The P-47 Thunderbolt emerged with the massive Pratt & Whitney R2800 engine, giving it exceptional dive speed. The P-51 Mustang arrived with laminar flow wings and the Rolls-Royce Merlin, achieving sustained high-altitude speeds critical for bomber escort. On paper, the Mustang became the world's premier long-range fighter, but even its top performance signaled a plateau. The fastest piston engine fighters could push into the mid-400 mph range, yet compressibility buffeting awaited any attempt to break through the next threshold. Germany faced a different kind of pressure. By 1943, Allied bombing crippled the Reich's industrial capacity. Interceptors needed not just power, but unmatched climbing speed and attack velocity to penetrate tight bomber formations. In response, German engineering shifted toward radical solutions. Some projects were desperate, others visionary. Jet propulsion promised the largest leap. Rocket propulsion promised an even larger one. Both systems bypassed the inherent limitations of propellers, drawing their power not from pushing air, but from accelerating mass through high-temperature exhaust. Each new aircraft represented a wager placed against time, resources, and collapsing infrastructure. Japan faced its own challenges. The Zero excelled early in the war, but structural fragility and limited engine development blocked attempts to follow the acceleration race of the late war period. Efforts such as the J-2 Raiden offered better climb speed, but none reached the velocity frontier emerging in Europe. The Soviet Union produced fast fighters like the Yak-3 and the La-7, yet their design philosophy prioritized low-altitude agility over top-end velocity. Across all nations, the fundamental question became unavoidable: which machine could break through the boundaries of piston engine aerodynamics and claim the title of fastest operational aircraft of the war? As 1944 approached, that question moved from laboratories into active combat. The skies over Europe became the testing ground for new propulsion theories, new materials, and new risks. Each country pushed its fastest designs forward, seeking an advantage that could shift the trajectory of the conflict. The pursuit of speed had become both a technological ambition and a tactical necessity, setting the stage for the machines that would redefine aerial warfare. The transition from piston engines to jets marked the most dramatic shift of the war's final years. Germany's investment in jet technology had begun long before the conflict, but wartime urgency accelerated every project. The Me 262 became the centerpiece. Armed with the Jumo 4 axial-flow turbojet, it exceeded 500 miles per hour, an unprecedented figure for an operational warplane. Its design combined swept wings with twin-engine thrust, producing acceleration that Allied pilots described as impossible to match. Yet the program suffered from fuel shortages, engine reliability issues, and production delays. Even so, when the Me 262 appeared in combat in mid-1944, it redefined the upper limit of speed achievable by any operational aircraft. Parallel to the jet program, Germany pursued the rocket-powered Messerschmitt Me 163 Komet. Fueled by hypergolic propellants that ignited on contact, the Komet could exceed 590 miles per hour in level flight and far more during ascent. Its climb rate was unmatched in aviation history at the time, reaching bomber altitude in minutes. But the aircraft was dangerous to fly, extremely limited in endurance, and tactically inflexible. It represented pure experimental velocity, deployed in small numbers under dire circumstances. Allied nations explored jet propulsion as well. Britain introduced the Gloucester Meteor, the first Allied jet to enter service, though early variants lacked the speed of the Me 262. The United States built prototypes such as the Bell P-59 and later the P-80, both too late to influence combat in Europe. These projects signaled the approaching end of piston engine supremacy, but did not reach operational maturity before the war's conclusion. Within the piston category, several machines pushed performance further than their predecessors. The Hawker Tempest achieved remarkable low-level speed, aided by aerodynamic refinements and powerful engines. The late-war Spitfire Mk XIV, powered by the Rolls-Royce Griffon, reached velocities beyond 440 miles per hour. The German FW-190D9 added altitude performance to an already formidable design. On the American side, the P-51D and P-47M represented the peak of U.S. engineering, with the P-47 Hitam capable of more than 470 miles per hour in level flight. Yet none of these fighters could match the raw velocity of the fastest German experimental designs. The war's final year revealed a set of aircraft that pushed performance far beyond the constraints of propellers. The Me 262 dominated the jet category, while the Me 163 pushed into rocket engine territory. These machines emerged from a collapsing industrial base, reflecting a technological ambition that outpaced Germany's capacity to sustain the war. The story of speed in World War II is the story of this transition, an intersection of aerodynamic innovation, strategic desperation, and shifting air power. This transition sets the foundation for the different angles that reveal how each aircraft earned its place in the hierarchy of velocity, and how the pursuit of speed shaped the air war's final phase. The human angle frames the experience of speed in terms of pilots' perceptions. For Allied aviators accustomed to propeller-driven combat, encountering the Me 262 produced shock. Reports describe the jet appearing suddenly, overtaking formation elements in seconds, and disappearing before pursuit could begin. Pilots trained in energy management struggled to adapt. Doctrine designed for piston engines collapsed under the jet's acceleration profile. German pilots faced their own difficulties. Transitioning from piston to jet flight required new approaches to throttle control, landing procedures, and engine handling. The Jumo 4 punished rapid throttle changes and failed frequently. Even so, those who mastered it described a sensation of liberation from aerodynamic limits that had defined aviation for decades. The tactical angle reveals how speed altered battlefield logic. Me 260's velocity gave it the ability to dictate engagement terms. It could attack bomber formations from the rear, use its speed to break through defensive gunfire, then extend away before escorts could respond. This changed the tempo of aerial combat. The Komet's speed created a different tactical challenge. Its rocket motor provided only minutes of powered flight, requiring escorted bombers crippled Axis infrastructure, allowing ground forces to advance. Speed became part of a larger system rather than a standalone asset. The enemy perspective demonstrates how each side interpreted the other. Meanwhile, the Komet's operational role faded. Its volatility, limited endurance, and dangerous landing characteristics reduced its missions to symbolic displays rather than measurable impact. The climax of speed in World War II. The war's fastest aircraft revealed the limits of human reflex.